Welcome to today's paper reading. Today's paper is titled, AI Agents That Matter. This paper was published by Sayash Kapoor and colleagues from Princeton University. The abstract highlights several critical issues with current AI agent benchmarks and evaluation practices. Firstly, there is a narrow focus on accuracy, which leads to unnecessarily complex and costly agents. This has resulted in mistaken conclusions about the sources of accuracy gains. To address this, the authors propose a new goal of jointly optimizing both cost and accuracy, and demonstrate a method to achieve this. Secondly, the benchmarking needs of model developers and downstream users are often conflated, making it difficult to identify the best agent for a specific application. Additionally, many benchmarks lack adequate holdout sets, leading to fragile agents that overfit to the benchmark. The authors suggest a principled framework to avoid overfitting. Finally, the lack of standardization in evaluation practices results in a pervasive lack of reproducibility. The authors hope that their proposed solutions will lead to more useful agents in real-world applications. In this paper, the authors discuss the definition of AI agents, emphasizing their interaction with complex environments and the pursuit of complex goals with reduced user supervision. They highlight the challenges in evaluating these agents, particularly the need for cost-controlled evaluations and the importance of jointly optimizing accuracy and cost. The paper makes several key contributions, including the introduction of new baseline agents, the use of Pareto curve visualization for evaluation, and efforts towards standardization and reproducibility in agent benchmarking. In this section, we discuss the necessity of cost-controlled evaluations for AI agents. We highlight that while maximizing accuracy can lead to unbounded costs, as seen in repeated calls to language models and majority voting strategies, this approach can significantly increase accuracy but at a high computational cost. We then introduce the concept of visualizing the accuracy-cost trade-off using a Pareto curve, where we reevaluate the accuracy of several agents and compare them to simple baselines. Our findings reveal that simple baselines often outperform complex agent architectures in terms of both accuracy and cost. This suggests that the community's focus on complex System 2 approaches may not be justified by the evidence, and that cost-controlled evaluations are essential for meaningful progress in AI agent design. Figure 1 illustrates that our simple baselines provide Pareto improvements over state-of-the-art, SOTA, agents in terms of accuracy and cost. We conducted 5 runs for each agent and reported the mean accuracy and mean total cost on 164 human eval problems. Notably, the simple baselines achieve similar or better accuracy at significantly lower costs, sometimes differing by almost 2 orders of magnitude. This suggests that the effectiveness of complex System 2 approaches for code generation remains unproven, as they have not been adequately tested against these simple baselines. The concept of visualizing the cost and accuracy of agents on a Pareto frontier introduces a new approach to agent design. This method allows for the joint optimization of cost and accuracy, which can result in agents that are less expensive while maintaining their accuracy. This approach is not limited to cost and accuracy. It can be generalized to other aspects of agent design, such as latency. The total cost of running an agent is composed of fixed and variable costs. Fixed costs are incurred during the initial optimization of the agent's hyperparameters, while variable costs are incurred each time the agent is used. Joint optimization enables a trade-off between these costs, allowing for upfront investment in design optimization to reduce the variable cost over time. This concept is illustrated through the modification of the DSP framework and its evaluation on the Hotpot QA benchmark, showing that joint optimization can significantly reduce costs while maintaining accuracy. Figure 2 illustrates the impact of joint optimization on agent design, showing that it can significantly reduce costs while maintaining accuracy. For instance, GPT 3.5 sees a 53% decrease in variable cost, and Llama 3-70B experiences a 41% cost reduction, both while preserving accuracy. This is achieved by optimizing the number of few-shot examples included in prompts, contrasting with DSP's approach, which includes up to 8 examples without cost consideration. In model evaluation, the primary goal is to identify improvements in accuracy resulting from changes in training data and architecture. This process avoids considering dollar costs to maintain the integrity of benchmarks, focusing instead on metrics like parameter count or compute usage. Conversely, downstream evaluation is driven by practical considerations, such as choosing the most cost-effective AI system for a specific application. Here, the actual cost of running the AI is crucial, and the evaluation must adapt to changing costs over time. A case study of the novel QA benchmark illustrates the challenges in designing benchmarks that accurately reflect both model and downstream needs. The benchmark, while suitable for model evaluation, fails to account for the real-world cost implications of sequential queries, leading to misleading results for downstream developers. This highlights the necessity for separate or variant benchmarks tailored to downstream evaluation. In this section, we discuss the issue of overfitting in agent benchmarks, which is a significant problem due to their typically small sample sizes. Overfitting can occur when agents use shortcuts, such as lookup tables, to achieve high accuracy on benchmarks, which does not translate to real-world performance. We categorize benchmarks into different levels of generality: distribution-specific, task-specific, and domain-general. Each level requires different types of holdout sets to prevent overfitting. While it is challenging to model all possible distribution shifts, benchmark developers must strive to create holdout sets that reflect real-world variability. Additionally, evaluating agents through Sim2 real transfer can provide a more realistic assessment of their capabilities. Table 1 outlines the appropriate holdout sets for different levels of generality in agent benchmarks. For distribution-specific benchmarks, the holdout should include in-distribution samples. Task-specific benchmarks require out-of-distribution samples to account for potential distribution shifts. Domain-general benchmarks should hold out specific tasks to ensure the agent's ability to perform well on unseen tasks within the domain. The table also provides the number of benchmarks with appropriate holdouts for each level of generality. The paper identifies 5 root causes for the lack of standardized and reproducible agent evaluations. These include evaluation scripts making assumptions about agent design, repurposing LLM evaluation benchmarks, and the high cost of evaluating agents. Additionally, agent evaluation often relies on external factors and can lead to subtle errors, and the lack of a standardized evaluation framework can introduce bugs in agent development. These issues have significant implications, such as misleading downstream developers and imposing a high time cost on researchers. The paper emphasizes the need for a standardized evaluation framework to address these shortcomings. In the conclusion, the authors highlight the nascent state of AI agent benchmarking, where best practices are still being developed. This makes it challenging to discern genuine advancements from mere hype. The author's thesis posits that AI agents are sufficiently different from models that current benchmarking practices need to be reconsidered. They have initiated a principled approach to agent benchmarking, proposing several recommendations. These include conducting cost-controlled comparisons, separating model evaluation from downstream task evaluation, and preventing evaluation shortcuts by using appropriate holdouts. Additionally, they advocate for greater standardization in evaluation practices. The authors hope that these steps will enhance the rigor of AI agent evaluation and establish a solid foundation for future progress in the field. Thank you for watching.